This is problem 18-24. A 15 kilogram uniform cylinder, 800 millimeters in diameter, rolls without slipping on an inclined surface as shown in the figure. A cord wrapped around the cylinder is attached to a spring having a K constant of 150 newtons per meter. If the cylinder is released from rest when the spring is stretched by 1 meter, determine A, the speed v, and the angular velocity omega of the cylinder when the stretch in the spring is 0.5 meters, and B, the stretch in the spring when the cylinder is again at rest. Okay, so at least visually, this problem doesn't have too much that we have to think about. There's one spring connected at the top of the cylinder by a string, and it's on a ramp at 40 degrees. So really, it's just interpreting the visuals and setting up the mathematics. So let's take a look at this. Let's first start with the free body diagram. We've got our cylinder. We've got the force of the spring. We have our force of friction. And this is going to be rolling, so it'll probably be a static friction of some sort. Okay, we have our weight of 15 kilograms times 9.81. And by the way, this is the force of the spring, which is equal to the spring constant times the distance delta. And then we have our normal force with the ramp. If we're to use the work energy equation, then let's go ahead and write this out, and let's tally up the various terms and what we'll need to actually take into account. All right, well, the initial kinetic energy, according to the equation, should be 0 because the problem does say if the cylinder is released from rest. So we're good to go with T sub I. Now, our potential energy may or may not be 0 because we do have a spring. And the problem does say that the spring is stretched 1 meter. So we're going to have a potential energy that we're going to have to calculate initial. And chances are that, well, it says here in part A, the spring, what is the speed v and the angular velocity of the cylinder when the stretch in the spring is 0.5 meters. So there will still be a potential energy left final. So we do not have zeros for v sub I and v sub f. Work done, well, the cylinder is moving down a ramp, and gravity, a component of the gravity, will be moving in the direction down the ramp. So gravity will be doing work. The normal force will be doing no work, but the friction and the spring will be doing work because they are pointed in the direction of motion of the cylinder. So we'll have quite a few work terms that we're going to have to calculate. And then the final kinetic energy is, well, they want us to find the speed in part A. So that's implying that there will be a final speed and therefore a final kinetic energy. So the only term that looks like it's going to be 0 is looking like it's going to be the potential energy. But let's find out. We got to dissect this problem a little more carefully. So let's look at how the kinetic energy works in this problem. We have this cylinder. Now, we have two types of motion. We'll have the linear, 1/2 mv squared, but we will also have the rotational kinetic energy of the, well, hold on, sorry, 1/2 the rotational inertia times omega squared. So this, I just want to point something out, that when we do some of the forces, we have ma for linear forces. And then when we do some of the moments, we have I alpha for rotational moments. And there's a similar kind of theme going on here as there is for the kinetic energies. The mass is kind of being taken into account by the rotational inertia. I mean, mass creates a momentum. It's just that we're talking about, for the sum of forces, a linear motion, the motion in a straight line. And then here, the rotational inertia is also a momentum, but it's only for the spinning element. And then, on top of that, you have an acceleration for the ma here, but that's a linear acceleration. And then this is an angular acceleration. So you have these terms that are very similar. Well, here you have a mass and you have an ig. And so you have your rotational momentum and you have your linear momentum, or your inertia, okay? And then here we have a velocity linearly and a velocity angularly. So I just, if you haven't noticed that pattern with these equations, this was my opportunity to kind of point that out. Okay, so now we can actually do a little bit of mathematics here, and we can combine these two terms into one term technically. How do we do that? Well, we can calculate the moment of inertia, and we can convert our angular velocity into a linear velocity. So what does that look like? Well, the next term would end up being the 1/2 mv squared, but then we'd have plus mr squared. It's supposed to be an m. Let me make that look a little better. Mr squared over 2, so 1/2 mr squared, and also times our velocity over r all squared. Well, where did that come from? Well, this term is omega. This is the linear to angular velocity transformation. So that should be pretty obvious by now, I hope. And then the 1/2 mr squared is going to be the rotational inertia of the cylinder. So there we go. So now what we do is, oh, and I missed a term here, and all of that is divided by 2 because there's already a 1/2, okay? So now we can combine, we have terms that are all in the kind of in the same ballpark here, that are all the same type. We can actually end up canceling out the r squareds, and we have a velocity squared now, and now we have 1/2 mv squared plus 1/2 mv squared, but this one's divided by 2. What does that all add up to be? 3 mass times the velocity squared over 4. 3/4 mv squared. Okay, we have a linear version of both the linear and angular kinetic energies. Great. So that simplifies the calculation quite significantly for the kinetic energy of the cylinder. All right, next, let's look at potential energies. So we're going to have the potential energy of the spring, and that spring constant is 150. Oh, and we need the 1/2 because it's 1/2 k delta squared. And then the stretched length is 1, so that's the delta squared. All right, now, next is there a potential energy for the gravity? Well, yes, because we know where the cylinder is starting and where the cylinder is ending. So what we need to know is what component of the gravity is moving along the ramp. And of course, then the other component is moving perpendicular to the ramp and doesn't count. So we actually want, and let me do a little color coding here. We actually want to know this orange component, and we don't need to know this blue component of the weight. The orange component is moving in the direction of the cylinder. And we can calculate the energy or the work, and both of those are calculated in joules. And so we can choose, since we know where the object is starting and where the object is ending during this problem's calculation, we can then decide, well, I'll just talk about the potential energy that the cylinder has from the beginning to the end, since I know where the end is going to be. But you could also calculate this as a work. They're kind of the same thing. So you might see some examples being done where you'll see this term that I'm about to write be as a potential energy, or it might be presented as a work, but it's the same thing. So I'm going to put it in the potential energy calculation, and so we're going to have 15 times 9.81 times the distance, because we're going in the opposite direction, but the force is pointing in the opposite direction of motion. And then sine 40 degrees because of the angle, 40 degrees because of the ramp. And then that is our potential energy for the gravity, since we know the distances. So, does the force of friction do work? Well, something that might not be immediately obvious to everybody is that since this cylinder is rolling without slipping, the bottom of the cylinder that is acting like a wheel is actually at a point of instantaneous zero velocity, meaning that for this moment that the cylinder is in contact with the ground, that surface of the cylinder is not moving. That might be difficult to wrap your brain around until you've thought about it for a minute, but you could just take these facts in for now and try and build an intuition around the facts over time, and that a wheel rolling does not slide. Therefore, there is no motion with the surface of the wheel in contact with the ground. Therefore, force times distance doesn't apply in this case, and the friction is not actually moving the object that the friction is being applied to. Therefore, the friction does no work. So really, when it comes down to it, you can be made to have a zero value in this particular problem. Normal force doesn't do any work. The friction force doesn't do any work. The spring is potential energy, and even the gravity is considered potential energy in this case because we know the beginning and the ending position. So we had no work terms actually to deal with in this calculation. So technically what I have written down here is what's on the left side of the equal sign. So only v sub I had a term. So I'm going to treat this as the entire left side of the work energy equation. And let's just bring this over a little bit. And I didn't mean to bring that chunk. Put him back. And so now let's do the right-hand side of the equal sign. Well, our final kinetic energy is next. And we already have a value that I had calculated for general kinetic energy of the cylinder. So let's go ahead and move the values in as necessary for that. So 3/4 times the 15 kilograms, and then the velocity squared. And we don't know the velocity. In fact, that's what part A is asking us to find. Next, we need to calculate the potential energies final. Well, in general, we'll have the potential energy of the spring is 1/2 of the spring constant, and then the distance squared. So that's the delta. And also we'll have gravity at 9.81, and then times -x/2 sine 40 degrees. Now, why x/2? Well, because when the center of the cylinder moves a distance x/2 down the incline, the spring is stretched an amount of x. Why? Because the center of gravity will be G at this location, the wheel will roll, and the rotation will, this is really hard to do on a static screen, but just realize that you have double the distance here. And so as the wheel rolls, when you move in direction 1 unit, the top of the cylinder will have actually rotated further, and so the spring will get stretched twice the distance that the center of gravity will have moved, okay? Because of the double lever arm. Instead of a radius, it's a full diameter. All right, so that's where the x/2 is coming from. And that does it. So that is the final kinetic energy and the final potential energies. And now we can reduce this equation down. And so they tell us that when the spring is stretched 0.5 meters to find the velocity and therefore find the omega. So we plug our 0.5 in for our x terms, and then we can solve for v. So the velocity is equal to 1.702 meters per second. That's supposed to be a 2. And then we can find our omega by using our velocity and the length of our radial arm, and that ends up being 4.26 radians per second. All right, so that is part A. And then part B is asking us to find the stretch in the spring when the cylinder is at rest. All right, well, this is a little bit simple and tricky at the same time. So our equation, our work energy equation, basically says that the final kinetic energy will be 0. So you can just kick this guy out, set to 0, and then resolve the equation for x, because now x is the only term not there. So we will then get x, so this is part B, x is equal to negative 0.369 meters. However, this is kind of a strange solution because the rope cannot be compressed. It can't hold a compressive force. It's not rigid. So the spring will go slack and won't actually start pushing back when it gets to the compressed state. So the cylinder stops moving with when the work equation gives a different value. So therefore, when the spring gets to 0, the spring no longer is a part of the equation. And what you want to do is then only include the terms here and here and solve for x. So give it a try. X equals 0.586 meters when the spring goes to 0 and then the cylinder has to roll to a stop due to gravitational forces only, not the spring forces.